Balko. I'm with Nordson Medical. So I'll give you guys a little bit of background on Nordson, and then we'll go into some details around flexible, steerable catheters and some design considerations when you're developing those. So Nordson Medical is broken up into 3 different focus groups. So we have our design development team, which is a broad range of engineers that we've got spread out globally in all the key device innovation centers across the world. So on staff, we have over 250 engineers and technicians dedicated just to new product development. Everything we do is development for our customers, so it's nothing for our own devices. So everything we do is on a custom basis for our customers. We sign all IP to our customers, and we don't own any of that on our side. So we're strictly a contract design firm from that regard. We also have a components and technologies portion of our business, which has best-in-class suite of different component technologies, as well as a really good team of application engineers to help integrate those into your new product development. And then the last group is the finished device solutions business, which really takes a lot of our global presence and integrates that into a full-service manufacturing offering. So that's for anything from finished devices to complex sub-assemblies, for things ranging all the way from components up to fully packaged, sterilized, private labeled medical devices for our customers. So this slide here has a snapshot of a lot of our component technologies. There's kind of 3 key things that we focus on with this. The first is speed to help our customers develop quickly. So a lot of kind of what we call project accelerators. So we've got an online store with several thousand components that you can get next day delivery on for all these different components that you can integrate into your new development programs for a lot of components specialized for interventional technology specifically. So you can see kind of a summary of the different components we have there. We also have world-class manufacturing capabilities. So the focus for all of our teams is on manufacturing and quality on the back end. So our process capabilities for all of the tolerances we can hold for these components, the wall thicknesses we can hit are all really state-of-the-art. So this here gives you a snapshot of kind of our overall global footprint. Nordson Medical is comprised of 15 different facilities located. We've got 10 domestic and 5 OUS. As you can see, we've really got that split out to focus on a lot of the key innovation hubs. So the Bay Area, Southern California, Colorado, Minneapolis, Boston, Ireland, and Israel. So we have both development facilities and manufacturing facilities spread out across the globe. So I guess the takeaway there is the overall size and scale allows us to have a lot of flexibility for how we structure our development programs, but also a lot of scale to help support the ramp up on the commercial side with high volume manufacturing as well. And then getting into some of the specifics regarding design and engineered shafts. So we have a wide range of capabilities. We can go into some of the design considerations that we look at on the front end when we're speccing out developing a new program for our customers. So we do anything from early stage concept development work with our clients all the way up through full-scale manufacturing. And we can engage anywhere in between. So we've got a product development process that allows us to split out and focus on finished devices as well as component assemblies and to tailor fit our projects for our customers. So we'll go through some of the key considerations we weigh into and kind of how we approach these programs. So some of the key performance features that we want to look at when we first engage in a new development program is tensile strength, compression resistance, ovalization resistance, flexural rigidity, torsional rigidity, and then the overall profile of devices. So we'll cover some of our capabilities and how we address these factors in the next couple slides here. So when we're looking at tensile strength, we've got a lot of different options for how we put reinforcement into catheters. So we've got, within Nordson Medical, we have a number of 16 carrier, 32 carrier, 48 carrier braiders, as well as a lot of coil winding capabilities. So we can do continuous coil winding, discrete coil winding, and we can also point wind coils, which allows us to actually deflect the coil directly onto the assembly, which can be beneficial when you're looking at how you terminate that inline. If you want to have, say, just a coil reinforcement section and a small deflectable portion of your catheter, we can actually deflect that wire directly on, so we don't need to transfer that over, which is kind of a unique capability that we offer. We also have, with the tensile strength improvement, we're able to run what we call triaxial wires, so we can actually run wires through the braid, so in between the eyelets, in kind of the over-under of the braid, we can string wires through that in line with our braiding capabilities. So that can give you a lot of tensile strength, but you also have to weigh in some different considerations on how that impacts your flex performance. So we can also do, like I said, we have the braiding and coiling. We can do multi-layer, so we can lay up braid and coil, which can come in really handy when you're looking at, say, a delivery system for a structural heart application. If you want to have really high tensile strength, but really good compression resistance for like a push-pull system, that allows us to be able to make devices that are really resistant to compression, so you don't get that buckling effect as well. So outside of that, we also do have capabilities for encapsulation of laser cut hypotubes. So that's another option for a reinforcement. For ovalization resistance, this is another key factor to consider. So the challenge a lot of our clients see is when we're developing the delivery system for their novel technologies, they'll have a lot of concerns with really high deployment forces and really high force to flex requirements. And one key driver for that is having something that's too stiff, too hard to flex. So that's something that we can help design around to make sure that the catheter has the right level of stiffness, say on the proximal end, but we're able to keep the distal end force to flex low and the force of deployment low. So one key thing to look at there is how we minimize ovalization, and when we're getting into some of the distal anatomies, to make sure that we have the right hoop strength in the catheter to make sure we're not getting any buckling or kinking of the distal end of the catheter when we're deploying our customers' novel technologies. So what we can do with that is all of our equipment is set up from the braider and coiler standpoint to allow us to do variable pitch braid and variable PPI coiling. So we can map that so that we can have different performance features on one end of the catheter than the other end. We can also use coils to make sure that we have the proper amount of hoop strength on the distal end, but you do lose something in terms of torque response when you move to a coil. So there's different things we can employ with using multiple layers of coils to give you a similar performance to a braid, but perhaps better crush resistance or better kink resistance, tighter bend radiuses. So there's a lot of different options we have. We also run a lot of different wire types, so we can do stainless steels, round wires, flat wires, any different fibers that you would want to use if you have different requirements for like MRI compatibility or things like that. So a lot of different options in the reinforcement front. And then looking at the torsional rigidity, that's kind of the opposite effect, right? We want to make that as stiff as possible typically. So a lot of technologies when we're developing, our customers want to have as close to one-to-one torque response as possible. So we do have a lot of different options in terms of what polymers we can use for laying up these catheter assemblies. So we do all sorts of thermoplastic extrusion in-house. We've got extrusion capabilities in 4 different facilities. So we can do things like PEEK that are really, really rigid that help with torque response, some high durometer nylons and different copolymers. We can also do a lot of different urethanes. And that goes the other way too for the flex performance. We can go really low down to some elastomers that are sub 80A type durometers. So lots of options there. One critical feature that we are able to support is what we call a strike layer. This can be a huge improvement for torque response. So a lot of times where you end up with issues and slippage is you have your reinforcement layers directly over the PTFE liner, and that now doesn't have any of that top layer encapsulating it well. So you kind of run into some limitations with how dense you can get in your wire reinforcement. Once you get up to the 60-70% surface area coverage, it really becomes a challenge to get good lamination between those layers. So what we're able to do is actually put a really, really thin skin layer of thermoplastic material on top of the PTFE liner. And what that allows us to do is lock that braid or coil reinforcement in between two like materials, which actually gives you a significant improvement in the torque response of the system as well. So that's a summary of that. And then for the flexural rigidity, as I said, this kind of is counterintuitive for how this plays off of the torque response. So as you're getting stiffer and stiffer materials, you start to lose stuff on the flex side. So what we have is we have a software tool that we use called SimShaft. And what that does is it allows us to get some quantitative data on how we anticipate these different key performance features playing out when lined up side by side with one another. So it allows us to kind of create a baseline and then look at quantitatively how do we think that a change to that design is going to impact the performance of the catheter. So that allows us to really get a good understanding before we kick off and start doing development work, how we think the results are going to play out when we stack up the torque response, the tensile strength, the kink resistance, the flexibility of the system. It allows us to have a really good data and starting point for how we want to start developing those systems. And then lastly, the profile. I mean, everybody wants to keep making things smaller and smaller, so that's always a limit we're pushing. And I mentioned earlier, we do have a lot of investment and focus on making sure we've got state-of-the-art manufacturing capabilities for laying things up, having very, very thin-walled offerings for our customers, but also having the process capability to be able to repeat that and transfer that into manufacturing. So these are some of the key features we look at when we're developing a new reinforced shaft. Again, we engage anywhere from very early stage development all the way through manufacturing transfers and full-scale manufacturing.